All right, so last time I presented the bare bones Grover algorithm. Where we had a function a that was 1 on some number a0 and 0 otherwise in a long list. And showed how to, if we had an oracle, a quantum circuit that enabled us to compute this thing, this function, then we could identify the value of a0 of order square root of n calls to the oracle. So that was last time. Today I want to do 3 things. First of all, make a bridge between this kind of very abstract, bare bones formulation of what the algorithm does and something closer to practical use of it. And some interesting points will come out of that, including an interesting perspective on the many worlds interpretation of quantum mechanics, I think. And then in the second part, I will demonstrate the optimality under certain conditions. And then in the third part, I will make a few concluding remarks about the whole problem of quantum search and question the optimality. So, because it's such a basic result and so foundational in the whole subject of quantum computing, and also since it's kind of a disappointing result to get only a quadratic setup, we really want to question every single assumption that goes into this proof and see if we can somehow find a way around it. Okay, so uses. First thing to say about uses is that there are many variants of the basic algorithm, which I won't describe, but I should mention that they exist, and there's references in the notes to where you can find out about these. They do things like, if you have not just one solution, one thing you're searching for, but search for M, say, M ones among a big list of ones and zeros. You're satisfied to find find one successful instance, then you can complete the search in square root of n over m. Using similar tricks. You can also, if you don't know in advance how many successful candidates there are ways of estimating them. And other refinements of that general character, that you can relax this abstract framework somewhat. But now I'd like to, as I said, having mentioned those, I'm not going to prove them or elaborate any more on them. Go back to the original setting where one has a unique solution. and ask what is a practical potential application. And the original application is something called database search, where you have a prepared listing. So the kind of thing that Facebook might have, where you have the many, many users' names, and attached to each user's name is a lot of information about them that you sell to people. Okay, and suppose you want to search that enormous list for a particular person, so you can sell things to that particular person. You find out that that person has just won the lottery. So you want to find that person in this gigantic list. What you do is tell your oracle look for, so you're going to look through your list of which attaches numbers to names and then other information. A database. So you look for cases, look for addresses where the name matches your target name, say Jane Doe. And there's going to be only one such case, and you return the number 1 if, when you look up what's at register A, you find Jane Doe under name. And 0 if you find anything else as the name. And that gives you then an oracle which is exactly of this structure. So the oracle is going to return 1 or 0 depending on whether you find Jane Doe or not. And you run the Grover algorithm. Sorry, was there a question? Or there's a noise outside, I guess. Okay. You run your algorithm, and if the list is big N big, after square root of big N calls to the oracle, you find what the address is where you can find where Jane Doe's records are filed. So now we have this set up for the Grover algorithm. We find A0, and then we can use A0 to get all the additional information. We use A0 as a pointer now, and all the other information about Jane Doe becomes accessible. So that's database search. Okay, you have a huge database you search on. an identifying field, and then you can retrieve the other information. Now, this is not a very good use of the Grover algorithm. Why? Because it takes a long, long time to set up this database, much, much longer than it takes to search it. So the limiting difficulty is not searching the database, but setting it up in the first place. Unless you do many, 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 many queries, gaining time in making queries is not going to be an important improvement. It might be that you will make many, many searches, and then it could be an important improvement, but in general, this is not the most promising or interesting kind of application. A more interesting kind is when the oracle computes some function. So this is what I called constraint satisfaction, as opposed to database search. When the oracle computes some function, chi of A, given A, and reports 1 if and only if chi of A satisfies some constraint. Or some requirement. Okay. Here the requirement was that the name matches Jane Doe, but you can imagine all kinds of things that might be required, including ones that don't require setting up a list in the first place, gathering a lot of information. I'll give a very compelling example momentarily. Okay, so there are applications in which you don't separately set up a database. You compute things on the fly, and then what's that? Yeah, for example, you might search for a prime number, or if come again? No, chi of A satisfies some requirement. So this is giving us again what we called F before. A function that's 1 on a very special value of A and 0 otherwise. So we're assuming there's one A naught that satisfies the requirement, the other ones don't. We want to find what A naught is. Okay, let me give an example that's actually quite profound. To fully appreciate the example requires some background in computer science, which I'm not going to supply here, but I will try to at least motivate it. In computer science, there's a class of problems called NP problems. NP stands for non-deterministic polynomial. These include things like traveling salesman, finding Hamiltonian graphs, that is circuits of graphs that don't ever touch each other, but don't ever cross, but do that continuously interpolate all the vertices of a graph once and once only, without self-intersections. And the problem I'm going to discuss concretely, the so-called satisfaction or SAT problem. Now, the remarkable thing about this class of problems is that there are a wide variety of them, including all the ones I mentioned, that are called NP-complete. That are equivalent in a precise sense, but imprecisely. Just equivalent means that if you found a good algorithm for one of them, you'd find a good algorithm for all of them, because you can translate, you can program one in terms of others. And the NP-complete, so that means in particular that they're essentially equivalent. If you have an algorithm that solves one of them, it'll solve all of them efficiently. You can use it to solve all of them efficiently. And again, all this can be made precise and has precise definitions that you learn about in computer science courses. But roughly speaking, the definition of an NP problem is that it's hard to find solutions but easy to check solutions. And let me, with that background, go to discuss the satisfaction, which will make all this, I think, much more concrete and clear. Yeah. There's a much more precise definition, which would, take half an hour or so to work through, and I don't want to pause for that. This is all very precise, but first you have to define Turing machines, you have to define polynomial versus non-polynomial, deterministic versus non-deterministic. And there are quite a few steps to making it all precise, but for our purposes, this is good enough. And this is only for background. We could just talk about satisfaction concretely, but the whole point of this is just that satisfaction is more interesting than it might appear, because lots of other things are equivalent to it. Okay, so satisfaction is the following. You are given a number of binary variables, or Boolean variables, I guess they're called, things that can be either true or false. Call them A1 up to A sub little n. So in the usual notation, they take the value 1 or 0 for true or false. I'll write it this way. And you're given propositions such as A1 or not A2 or A3. Okay? Propositions like this, a whole bunch of them. And the question is, can you find values, can you assign values to each of these variables such that all the propositions are true? Okay, so for this one to be true, either A1 has to be true, or A2 has to be false, or A3 has to be true, but you don't know which, so exploiting this information is not so easy. And if you have many, many of them, there are many, many possibilities, and checking that, well, it's very difficult. No one has found a good way to exploit that information in order to find solutions. In fact, the best known classical algorithms that are guaranteed to find a solution even given that a unique solution exists, aren't any faster than basically, are not significantly faster than just trying all the possibilities. Okay, just try them all. Right. No one knows how to do a lot better than that in general. Okay, there are tricks that'll work on special cases, but in general, there doesn't seem to be any approach that makes headway on this, despite a lot of effort. If you do find a way, you can become rich and famous. But on the other hand, it's very easy to check whether a proposed solution is true. You just stick in your values and see whether all the propositions in fact are true. It's a very, very rapid process. So it's hard to find solutions, but easy to check. Okay, now suppose we have an oracle that does the checking. Actually, the process of checking you can easily automate. You can easily imagine automating and design little quantum circuits that will do the checking. So this is not unrealistic to construct such an oracle with a reasonable number of gates. And then you can have it and report. So it does the checking and reports f of a equals 1 if the assignment that corresponds to the binary number a is a solution. Okay, every one of our assignments can be interpreted as a binary number, a number written in binary from 0 to n minus 1, big N minus 1, and 0 if not. And then we can run Grover algorithm on this. Okay, and our list was 2 to the n long. Our calls to the oracle take a relatively short time compared to 2 to the n, so we count that as 1 for this purpose. Therefore, Grover implies that you can do this in a way that depends, instead of on exponential of n, on exponential of n over 2. You get a square root improvement just by trying them all. Right? The oracle tries them all at once, so to speak, in using quantum parallelism. And clearly, if you could do better than square root of big N, it would have a big impact because it would also impact on this whole class of NP problems directly using that same strategy. Okay, are there any questions about that? Okay, so let me indulge myself by saying a few words about many worlds interpretation based on this. I used to be very fond of the many worlds interpretation of quantum mechanics, but as I've grown older and wiser, I'm less fond. So what does this suggest about that kind of question? Okay, how do we talk about, how do we interpret what's going on in this kind of situation? Well, you might say that it suggests that you should take the many worlds interpretation series as a good way of talking about this, because our oracle has somehow accessed every single possibility for the inputs and done a difficult calculation, not difficult, but non-trivial calculation based on every single one of those inputs, and all those calculations are significantly different. And it's done it in a time that it could not have done sequentially. It's taken the square root of n instead of n. So you might have asked, where did those calculations occur? And the only answer you can give is that they occurred in some parallel universe. They occurred, in the same space we live in, but in some parallel universe of concepts or parallel universe of possibilities. We need that to make room for the fact that all these calculations took place in a shorter time than there was room for in our universe, in one concrete classical universe. On the other hand, one can also make arguments on the no side. First of all, we don't have those answers. Okay, so in what sense were the calculations actually done? And if we introduce dissipation into this question, if there were really many, many parallel universes, there should be dissipation in all of them. And the dissipation or other properties like that don't add up. We don't generate a lot of heat from these extra universes. It doesn't take a lot of extra energy to run the different universes. So the reality of them is very tenuous. Okay, it certainly doesn't contribute to additive quantum numbers like energy. Well, if they all exist, where's this energy going? Or into other ways. Okay, let me put, maybe this is a better way to say it is, where is the energy coming from to power all this dissipation? Yeah, so our universe has to, since our universe is powering all this, where did the energy come from? Some other universes also need similar kind of energy to dissipate. But we're putting it in. Okay. You know, we don't need to put in extra energy to run all these extra universes somehow.
Is it correct to say that we are putting it in the same right?
Well, we're the people who have to plug in the computer. Yeah. Well, I think you don't, in other words, when you plug in your computer, you don't have to worry about powering the other universes, right? But even though you're driving events in them, in some, according to that interpretation. Right? Yeah.
Why is it not enough to say, well, instead of the classical beta, we have a Hilbert space, which is two-dimensional, which is a much larger object.
2 to the n dimensional, you mean? Yeah.
The
Right.
calculation happens in that.
Yes, that's right. Yeah, no, absolutely. I don't. That's not. Yeah, I agree with that. I think one has to take this kind of more abstracted point of view, because trying to take these many worlds literally leads to paradoxes. That's really what I wanted to say, is that I think the problem with the many worlds interpretation is that it's trying to interpret quantum reality in classical terms. You know, implicitly, you're being asked to take these other worlds seriously as implicitly classical other universes, or that's the temptation, and that won't fly. It leads to paradoxes. So I think it's better just not to talk about this, or to, if you do like to talk about it, and it's fun, to realize that these other worlds have a very tenuous existence. It's a very tenuous reality. Okay, so that's 30 minutes? Okay. Let's get started on the optimality proof, and then we can break. Okay. So, just get started. Okay, are there any questions, any other questions about this? Or? So that was part 1. Now I want to move on to part 2, the discussion of optimality. This is showing that under certain assumptions, you can't do any better than the Grover speed up going from n to square root of n.
I still have one question. Like this kind of SAT problem. You say that it belongs to that same class of problems that are sort of hard to solve.
Yes.
No matter what the propositions are, or is it just that?
No. Worst case. The worst case. Yeah. Sometimes you can get lucky and find easy cases, and there's no algorithm that's guaranteed to handle all cases.
Yeah. So it's like it's easy to look for even numbers rather than for prime numbers.
For instance, yeah. Right. I mean, that's not SAT, but it's that flavor. Yes. Some many satisfaction problems are easy to. In fact.
But can you not reformulate this problem in a kind of a number theory framework?
You can reformulate in all kinds of ways, right? But it doesn't help, you know, or at least no one has found a way to make that help very much. In general, okay. There are many special tricks and special cases that will enable you to find solutions. But they're not guaranteed to always work. Okay? And there's actually a lot known about these kinds of problems. There are even phase transitions as a function of the number of propositions, things like this. And it's near the critical point, in fact, where things get where it gets difficult. Okay, but that's a very interesting subject, but I don't want to go into it here. Okay. So now we're going to move on to the proof of optimality, And for that purpose, let me recall that we had we're going to go back to the bare bones Grover algorithm, and we have our oracle, which knows the answer is X. So the oracle, when the answer is X, is that one. And we have our reference state. Remember, I just want to recall what we've got. Square root of n. Of the number states. And I'll outline the strategy of the proof, then we'll break, then I'll give the proof. And conclude with some discussion of how the proof might not actually be a proof in the sense of bringing the field to a screeching halt. Okay. So the structure of the algorithm is to produce, remember, a wave function that looks more and more like X by making repeated calls to the oracle when the answer is in fact X. So we will abstract that structure, get the essence of that structure by defining a wave function psi sub k super x that we get by making k calls to the oracle, and then in between the calls to the oracle, applying some unitary operations. Okay? In the Grover algorithm itself, remember these unitary operations were reflections around the state S. But for the purposes of the proof, we don't need, we're going to show that no matter what you do in this framework, you're stuck. Okay, so the U's, since this algorithm is supposed to work for any x, are unitary operators that are independent of x. And then, on the other hand, we can have the comparison wave functions that we get by just not using the oracle. And the structure of the proof will be to show that since these oracles in general are not very different from the identity operator, they just affect one state in the whole Hilbert space, these phi sub x's can't be very different. The phi's with the superscript x's can't be very different from things without the superscript in general for all x, unless you apply the oracle many times. In fact, roughly square root of n times. So the structure of the proof will be to estimate this difference as a function of k and show that if you want a successful algorithm, it has to be pretty big. But on the other hand, for it to be pretty big, you need many calls to the oracle. Okay, so let's break and then we'll work through it.